It's a great honor to introduce Professor Michelle Addington. I'm Professor Forrest Meggers from the School of Architecture and the Andinger Center for Energy and the Environment. It's especially a pleasure to host Michelle here at the Andinger Center for Energy and the Environment Highlight Seminar Series. As she's regularly invited to the School of Architecture, but I think it'll be fun today with our sort of more interdisciplinary more interdisciplinary audience. Already seen colleagues from NIE, CBD, and also architecture, where we'll have the ability to facilitate perhaps an exploration into the challenges of understanding not just architecture and engineering, but perhaps a bit about architects and engineers themselves. Michelle is the Heinz Professor of Sustainable Architectural Design at Yale, where she's jointly appointed between the Yale School of Architecture and the School of Forestry and Environmental Studies. She is educated both as an architect and engineer with a BS in Mechanical Engineering from Tulane, a Bachelor of Architecture from Temple, and a Master's of Design and a Doctor of Design, both from the Harvard Graduate School of Design. In her role as an engineer, she has spent time at DuPont as a process design and power plant engineer. She's also worked at NASA's Goddard Space Flight Center. And as a professor of architecture, she has published extensively on energy systems, lighting, advanced materials, among many other fascinating topics. She's the author of the book Smart Materials and Technologies for the Architecture and Design Professionals. And in 2009, Architect Magazine selected Michelle as one of the country's top 10 faculty in architecture. And I've been very blessed to be able to interact with her in the last year and a half of my brief time back in the United States, and she's one of the most impressive people that I've met in my time back here, and one of the most inspiring people to have been able to learn from already extensively in that short amount of time. So I'm thrilled to have Michelle here as a mutant architect and engineer like myself. And for me, it's especially reassuring to see that someone can truly survive the competing realities of architecture and engineering and stay as friendly, engaging, intelligent, and most importantly, sane. And as always, I look forward to hearing her talk and hope to glean more wisdom from her on the disciplinary mistranslations happening between architecture and engineering today. So with that, thank you very much, Michelle.
I'm going to doubt that my ex-husband thinks I'm sane, but, and I also appreciate the kind things that you've said. I'm actually feeling quite the opposite of Forrest in that having met him about a year and a half ago, I was blown away by his sort of like smarts, his competence, his poise, but his ability to do stuff that, frankly, I can't do. And I'm feeling quite chastened by the fact that I'm up here and he's not up here, because I'd rather be learning from him than the other way around. So this talk is actually occurring at a time where there's sort of a perfect storm happening in my life that deals with disciplines. And the first thing that happened to me was that it's the 20th anniversary of my doctorate, and I had high hopes for this doctorate. What I was doing is I was trying to look at the shift in heat transfer technologies, heat pump technologies, heat pipes as they got smaller and smaller. And in particular, I was looking at what the Department of Energy was doing at the time, making a proposition about micro heat pumps that would be printed in a wallpaper. And their speculation at the time was that the sheet, a 1 meter by 1 meter sheet of micro pump wallpaper would move more than enough heat to heat or cool the average home. And then, of course, as they were working on it, and as I was doing my work, and within 2 years, it was 10 centimeters by 10 centimeters, and it was cheap. And then, of course, as I started this work, that meant the program would be canned. And when I talked to Pacific Northwest National Labs about why on earth would they can a program like this, it's cheap, there's so much I can do with this type of microscale movement. And they said, well, it's impractical for buildings because it can't replicate the conditions of an HVAC system. And I thought, that's bizarre that the 100-year-old technology should be deciding how you deal with a new technology. But nobody was actually really questioning the idea of homogeneous air. And so this is a sketch that they had, that they published. These were some of the early studies that I did with direct numerical simulation, which was pretty tough to do back 20 years ago, of how I could manipulate characteristic length and convective heat transfer. So I realized, the work went in a slightly different way. I was really disappointed to lose that opportunity to work in micro scale. And one of the reasons it's important to talk about right now is that I'm on sabbatical, and I started this sabbatical off in January thinking, I want to start this all over again, begin all of it. But of course, I've managed to find myself distracted by many, many other things, including committees that the university won't let me off of. But the other sort of second thing in this perfect storm of three things was that it's not quite 20 years, but almost 20 years ago that I put together and I taught the first course in smart materials ever taught in a school of architecture, and it's probably one of the first courses anywhere on smart materials. And I have transitioned it over the years. It's when I first started teaching that course in 1997. We didn't have any smart materials to work with. I had a sample of a photochromic that Polaroid was making, trying to save Polaroid. It was a sort of photochromic that basically went from brown to crappier brown, but it was, that's it. And then I actually had, my micro machine background and managed to put together an entire course on this where we had nothing. But talked about quite a bit of it. And of course, as that course went on over the years, my array of things sort of grew more and more. And I finally came to the point when I realized the students were up to speed. Survey is not what they need anymore because they were all doing their own experimentation. I switched it to a course that was just about looking at smart light, so only looking at materials that interacted with light or produced light. And then I just retired that course. And I'm working on a new seminar for the fall, sort of the next version. It's actually going back to something that happened that was written about in the book. And it sounds like a very old topic, but I'm trying to sort of bring something fresh to it. And it's sort of rethinking what we think of as the smart building. Because so much of the way that we're thinking about the smart building is actually smartening up the dumb aspects of it, as opposed to sort of rethinking them. And so I have this collection of things I've collected over the years about sort of images of smart buildings, particularly images of smart homes. And I was just sort of enjoying looking at these, and I'll just share them with you. This is the one, the Apple Home kit, locks, lights, thermostat set. This is Google Glass, your heat is set, unlock your door. This was Microsoft's Home of the Future. The front lights come on, the door unlocks. Philips' Home of the Future. This time it's a woman. The door alarm is switched off. It sort of unlocks and opens. This is the Tron version of 1987. From the moment that the employee arrives at work, the buildings recognize him, open doors for him. And I actually found one from and then this one from 1967 from Walter Cronkite. Adding in here about sort of like the fact that it should be sealed like a space capsule. That's actually sort of an interesting aside, is that when I first started teaching in this area for architecture, the number of people who would pull me to the side and say, if you're dealing with environmental systems for architecture, you need to look at the space station. Those people know how to design for an interior. I never mentioned, well, actually, I spent 3 years at NASA, but I did unmanned stuff. So, maybe that's what they were thinking. But it's bizarre when you imagine that something that is in a relentlessly hostile environment would be the model for how we might think of human occupation. But I haven't had that argument in a long time. But here's one that I found from the 1920s. So even in the 1920s, this somehow fascination with automation. And so much of what we've talked about in smart buildings relates to simply automating the quotidian, automating the banal, but not really rethinking what any of these things do. So I'm actually looking forward to, pulling this back together into a new course for my students this fall. But the third thing that happened, sort of pulling all this together, is that last fall, the science provost and I started talking about why it is we're having such a difficult time really moving forward on interdisciplinary research. It's not that we're not trying in many different ways, but something's not working. We're not able to really go after the big problems. We can do some nice small things. We're not going after the big problems. And I realized that, I had sort of functioned under different models. So when I taught at Harvard, I worked with a variety of pretty amazing people, but all of them I had to hunt down. In the case of George Whiteside's, just hang outside his office for a year. Roy Glauber, who got the 2006 Nobel Prize in Physics, actually was bored, so he was totally interested in talking about architecture. But all of these people were hard to find, hard to track down, hard to find a relationship with. And while my doctoral students who worked with these individuals, I'd say each one of them had some did a pretty remarkable project, think about them as being one-offs. Think about them as being somewhat idiosyncratic. Probably the most interesting project that came out was an electromagnetic paint that could strip out a particular wavelength of light and direct it toward the eye. She actually got a postdoc with NASA to develop and eventually patent that. I don't think anybody uses the paint, but it was such a great project, and the number of people who were involved in it, from neurobiology to visual psychology to physics, and actually Roy Glauber signed off on her dissertation, so I think to this day she's probably the only architect who's ever had a Nobel Prize physicist sign her dissertation. But this was not sustaining. This was really hard work, and it was just incidental and accidental that certain things came together. There were other collaborations here that just didn't work. We had a couple of nice conversations and went away. So Yale is exactly the opposite of Harvard. Yale is friendly. It's wildly collegial. Everybody talks to everybody else. And Yale, just in trying to have interdisciplinary, relationships, there is a center for everything. This is just a handful of the ones just at the forestry school, and that's just one page of them. It goes on and on and on and on. And I'm on the board of actually a number of these different interdisciplinary centers. I love the people at these centers. We enjoy each other tremendously, but somehow just having people as part of the same being contiguous with each other doesn't necessarily mean that anything interesting happens. And this is actually what the provost and I have been talking about, is how do you go, from these different models and actually start to pull out problems that are really interesting within that. And then, of course, as part of this, I've been reading, I'm sure many of you have read this report that came out from the National Research Council about interdisciplinary research. It came out about 10 years ago. And for them, it was all just structure, entirely structure, how things are organized. And I think that, my experience and my discussions with the provost on it is that, well, that might be a way, to sort of get people in the same room, but it doesn't deliver content. And content is really what you have to deal with. So what we're dealing with today is sort of understanding why it is that content has been so difficult for us to come to grips with, particularly as we're dealing with a field like architecture, and particularly as we're dealing with the technological science parts of architecture. One of the conversations the provost and I had about interdisciplinary work was where he said, I do think that we were also talking about faculty who operate and how they should get tenure and how you evaluate them. This has actually been another thing that we spent a great deal of time on. And he goes, it's not that hard. We often have microbiologists and molecular biologists, working together. We can do interdisciplinary stuff here. These are radically different fields if you think about architecture and if you think about engineering, and particularly mechanical engineering. There is sort of no commonality in approach, no commonality in method. There's also no commonality in content. We might think that there actually is no commonality on that. So I've been sort of progressively wrestling with, why aren't we moving along faster than we are? Where are those gaps? What are the questions that should negotiate those gaps? And while I'm doing this as a series of misses, so mistranslation, misattribution, and so on, I want to sort of, before I get into this, state that this is not a criticism of what's going on. It's more or less sort of laying out the territory of some missed opportunities. So all of the things that have been happening in these fields have contributed to our larger body of knowledge, but what we need to do is sort of find what those larger gaps are and ask questions. So something that is incredibly common in the teaching of architecture is something called the Precedent Study. You take a precedent, you look at the precedent will be a building. You usually be looking at the a monograph of the building, and you read about the building. It says it does this. You look at what it used, or you look at the drawings. You associate the two. So this is one of the most common precedents that you see in lighting design, and this is the DeMenil Museum in Houston, Texas. And this is this image that always accompanies this museum in a precedent study, and I probably have seen it well over 100 times in the years that I've been teaching, as students want to talk about how light works. They love this image, of this particular type of louver system, top lighting louver system. And, and of course it's explained in the monograph in a way. This image shows up, people recreate the image, they'll borrow the image and sort of like, or use the ideas from the image. And, every time I looked at it, I said, this is Houston, Texas. This is such a bad idea. It can't work like this. It can't be a good system. And so I got a little bit of funding, and I went down to see the roof of this building. And I apologize, I haven't ever digitized those images. This is done quite some time ago. But I was able to find something that at least sort of indicated what was going on. What happens is that the majority roof is completely covered over. There'll be tiny slots here and there that let a little bit of light in. The only place that's uncovered is actually over the lobby area and some of the corridors, and in sculpture, because sculpture is not sensitive to light. Everything else, it's either fully covered. If it's a visiting exhibition, it's double covered. And in other parts, it might be, partially covered. But again, the reality, it's not that reality. It actually is something completely other. And so I realize this is a huge issue for us in architecture because what has authority? Where do you get your information from? If these types of things have authority, you have no basis from which to sort of like question that authority. It's written about, it's been published for years. What do you do here? And I think this is one of our biggest issues. I often talk to students about the fact that if they're writing a paper in history and theory, they will cite their sources. If they're writing about technology, they don't bother to cite because anything in technology is fact. And therefore, it just sort of gets lifted as fact. And this is one of the areas of misattribution that we have to deal with. I say this is probably the area, the misassumption has been my biggest struggle of all. And I just came to a realization a couple of months ago about how to sort of deal with this. I'm not going to be able to try it until this fall when I go back to teaching. It might also be a disaster for all I know. But I've always been troubled about the fact that we are so obsessed with the facade, the envelope of the building, the facade of the building, that we do energy balances on a facade. We think about the insulating value of it. Everything that we look at in the facade. And of course, if you stepped at it from a pure thermodynamic standpoint, the facade is actually almost irrelevant in a lot of that. And yet it's the thing that we're most fixated on. And so everything is sort of understood through the facade, it's positioned through the facade. And as I was thinking about it, and actually this was just a couple of months ago, I thought, this is just a proposition. So those of you in architecture can let me know if you think that I might be onto something here. I realized it has to do with the one part of science that is inherently well understood in architecture, and somebody might disagree with me on this one. It's structures, statics. That I'm going way ahead. I'll come back to that one in a second. So hold that in the back of your mind. So this is one I should have had this sort of like going forward for me. So just remember that one. I'll be there in a few moments. Misassumption. This is an interesting case. The architect should recognize this is Louis Kahn's Center for British Art in New Haven. This was his last museum, completed after he died. Started while he was still alive, but completed after he died. And across the street is his first ever art museum. It's a really incredible collection of buildings right there. Actually, you can see the first museum right over here. So not too many years ago, Yale did an exhaustive renovation of the first museum, including adding features that had been value engineered out. The thought was we want to bring it back to the architect's dream, even though that dream hadn't been built. So they added those features back in. So the Yale Center for British Art shut down just a few months ago. And they decided they will do the same thing. So one of the things they had decided to do was fix the skylights because the skylights were facing the wrong direction. And so they called me, just sort of to talk a little bit about it. And here's the skylights, an image of the skylights right here. And they called me because of this particular book and conference that we had done. Richard Kelly was a lighting designer who designed all of Cahn's lighting, from the Kimball on, did all of Philip Johnson's, did Mies van der Rohe's US buildings, did all of Saarinen's buildings. I mean, this was the lighting designer of the 20th century. And one of the things that was in the exhibit and then also in the book were a transcription of his notebooks. And the notebooks said that, explain the skylight design. And so what the Yale Center for British Art had wanted to do was the skylights faced south. They thought the skylight should face north, and so they were going to, invert them when it was shut down. But when they were reading through the notebooks, they realized that, he explained in the notebook that they have to face south because there's less ultraviolet. And so they asked me to come down and explain to them how could that be so? How could a south-facing skylight, be less damaging to paintings than a north-facing skylight? And it was only a 10-minute talk. We talked a little bit about this. We looked at this, and I explained, on a lumen per lumen basis, we're going to have a whole lot less ultraviolet in south light. Not on a square foot by square foot basis, but on a lumen per lumen basis. And so it's fine. And so they've agreed they're not going to swap the skylights around, that maybe they were installed. They were installed the way that they were designed to be installed, and probably Richard Kelly was right on that. So this summer, I'm also on the board of our new Center for Preservation and Conservation, which is out at our West Campus, which is about 10 miles west. And one of the curators who had been at my talk on ultraviolet radiation and the skylight design wanted me to see the new skylights that they were putting in. And he showed them and says, and they face north in the proper direction. I said, well, didn't you hear my talk on this? And he goes, yes, but that was for the Yale Center for British Art. We're 10 miles away. So I thought, really, probably the sun is somewhat similar, 10 miles to the west. But he said, but this is the way skylights are always done in museums. They always face north. Every great, 19th century museum has skylights facing north. Well, every great 19th century museum really wasn't sort of aware of other types of things, plus also didn't have the array of lighting opportunities. But it was one of those assumptions that could not be shaken. We have many of those, many things that people believe to be so, that it's very hard to shake them away from. Okay, misinterpretation. This is the structures part, sorry about that. The thing that's really interesting about statics in buildings is that if you look at statics, you look at a structural diagram, you look at a building, it's one for one. You can enter into that type of understanding from any point. You can look at the structural diagram, you can look at the structure of a building, you can sort of deduce what the structural diagram must be like. You can look at a structural diagram and you can begin to sort of produce what might be a structural system. And we can see it all the way through. There's a direct relationship between the material artifacts, the forces. Even when something gets really complex, we can work it back and forth. There is that direct relationship for that. We want that direct relationship to occur for a thermodynamic system. People assume that direct relationship occurs between a thermodynamic system and and a building, in the same way it occurs for statics and a structural system in the building, that it's one and the same, that it's primarily about the material artifacts, and of course that the material artifacts are primarily going to be associated with the building envelope. So there's that desire for that. And that's why when people look at a thermodynamic diagram, they don't think about it as a window. They don't think about it as a view frame. They think about it as a container. They look at this as if there's a container, that there is some inside, there is some outside, and there is some boundary on it. So something like this, they simply just sort of plant on top of it a building. That's what a thermodynamic system is. It's exactly the same for a building, also read through the material artifacts, also read through the envelope on this. And so, you end up with things like this. This is one of my favorite images from James Marston Fitch. Doesn't matter what's happening, it doesn't matter what the phenomenon is. The envelope is the boundary crossing. So it's the same thing there. Everything must happen at that particular envelope. And of course, we have this entire trend that's gone on for many years in architecture on the smart skin, on the high performance building envelope, on the high performance facade, trying to make that facade do all the things that their image of a thermodynamic boundary tells them it should be doing. Control light, control heat, control air movement. All of those things are supposed to be happening. I think something else I also love about this image is this sort of idea that there's a homogeneous inside, you're blanketed in sort of like, basically I guess it could be the idea of a thermodynamic state because it's one pressure, it's one temperature, it's one density and so on, but sort of blown up in huge scale, that whatever is happening outside must be hostile because you don't want any of that coming inside unless it's been mediated, controlled, and mitigated or absorbed on that. So we end up with things that really we should think is, this is pretty damn bizarre. How could someone describe something like this and have it make any sense? That, you build tight and ventilate right, that there's no such thing as a house that is too tight. And that makes sense as long as you're thinking the building is a gigantic thermodynamic system with a closed, envelope serving as a boundary that things can only cross that, and that I got to contain the inside of it perfectly, then maybe this makes sense. If anyone has time later, one of the things I worked on at DuPont was spun bonded. I also know how this doesn't work even for that, but you can't disabuse anybody out there from using this on a building. But it leads us to things like this. There's a whole cult involved in this passive house, basically sort of the next version of the very sealed house. I mean, this is a description. This comes from the New York Times a couple of years ago. These houses are so airtight that warm air won't leak out in winter and won't leak, and cool air won't leak out. That's a bizarre way of thinking about cooling, to talk about holding cooling in. Cooling is about dissipation, not about sort of holding something in. Of course, they think about it as holding something in because we use an HVAC system, and therefore that's the image that's around it. There's nothing sort of very natural or passive or even reasonable about something like this, and yet everybody will argue for something like this. And of course, if you think about the idea that it is the container that matters, and it's this environment on the inside that you're conditioning, then the one thing that we know, and we all know this, is that the number one contribution to energy use going up, going to be going up dramatically worldwide, is that the larger the building, the more air that's being contained, the more air that's being conditioned. So you have a movement toward microhousing. Now this is a project in New York talking about microhousing. And I apologize if you've seen the next video. It's one that endlessly delights me, so I have to watch it over and over again. So let me see if I can just get this.
Hi, welcome to Tiny Town.
Micro village.
Little place. And that's a tiny micro house.
Yeah, it's very, very efficient.
Everything is thought out. No waste of space anywhere. This is a bathroom and a home office.
Can you hand me the shower gel, please?
Yes, coming up. There you go.
Thank you. How's your novel coming along?
Really great. I'm on page 1.5.
See this kitty litter box?
Out of sight. You have a library. Oh, hi. How's that book?
It's great. I just, wanted a little alone time. I'm just hanging out watching TV.
I'm just taking a bath. Oh, I'm ready to wash my hair.
I can't see the TV now.
What?
Can I shut it off? I can't see the TV.
Sure.
Kendall,
Hey,
I forgot the code to the door. Can you just come down and let me in?
I'm upstairs. Every little closet, every little space, every little cubby hole.
Micro living.
Thanks for making the bed. That was very nice. So what did you want, cream?
Yeah. Okay, you're always breathing down the back of my neck. It's like I can feel your hot breath on me all the time.
Mmm. Some French toast. There you go. Bon appetit.
So, okay. We've been to a micro house.
In a micro community.
So anyway, like I said, I probably have seen that dozens of times, and I enjoyed every single time. But, that's, dealing with this. If we really think that a building has to be a container of conditioned air, then the only way we can really think about seriously saving energy is simply to make it a smaller container. And that's sort of taken us into that sort of like nth level of being extreme on this. But if you go back and you really think about this, and you think about this not as a container, but as a view frame, I've looked for years to find a way that I could visually explain something to architecture students that's not visual. And a thermodynamic boundary is certainly something that's not visual. But I have a visual thing, and I haven't tried this yet with them. I'm going to put it in my class this fall. So you let me know if you even think this is a reasonable way to explain a thermodynamic boundary. So something very transient, something about discrete energy exchanges between different types of states, even though those are very large states. At least it gets that idea that it's transient, that it's not sort of like fixed to a location, that it's contingent. It's not a constituent thing, it's a contingent thing on that. Misappropriation. So this one comes from a couple of different places. And the first one comes from, this is the MRS material science meeting I went to last week. I think some of you were at this particular meeting in San Francisco. And what you're looking at here was a meeting between architects that did materials research and material scientists. So this was an architect's talk. And so this sort of idea of appropriating as much of the language as possible from the material science world. This is the one talk the material scientists had no idea what was going on. But if you go on the other side, sorry, I put this in the wrong order. If you go on the other side of it, and of course you know who this is from, this is sort of an idea of if the architects were trying to sort of adopt the language of material science, then we had the material scientist trying to sort of like shift into being an architect. And this is the Wyss Institute at Harvard. This is one of their major project areas. The long-range vision is to design entire buildings that adapt their shape and function to continuously optimize energy efficiency, thermal gain, and other properties critical for sustainability. Everything else is operating that they do, of course, is at nanoscale, but suddenly we're going to operate and do buildings. And every time I'm there, I have a conversation with Joanna. She explains to me that wouldn't you like a building that could respond to its environment? I thought, we've talked about this for decades, and there's reasons why we want it, and there's reasons why we don't want it. But, this is another image that she has shown me, and many of us over and over again. This is what houses should look like. They should look just like Radialara. And she also finds architects like John Johansson that have built things like Radialara, and why we don't get that this is what we should be doing, why we don't understand it. So this is a material scientist wanting to talk about architecture. And I realized as we had this sort of 2 days of conversations last week, that there was a series of places where we really weren't communicating, and perhaps the biggest place we weren't communicating was on the nature of scale. If you think about Linkscale, which is the sine qua non for material science, when we talk about scale in architecture, this is what we're talking about. We're not talking Linkscale, we're not talking about scaling laws, we're talking about size. That's a very different thing than scale. We're talking about number of units. We're talking about an abstract representational model, a model that was been built at 100 scale, not scaled physically at that level, but scaled abstractly at that level. We might be thinking about referential frames. I'm looking at a micro scale, which might be a room, and a macro scale would be, a region or a city. So we have all these different things. The one thing we don't have is Linkscale. It doesn't come into play. It is the one thing that really drives material science. And yet, when we talk about scale, when either side is talking about scale in architecture, they revert to this. The material scientists were talking about scale in this way, not talking about scale in the way that they deal with it. And of course, the architects, this is the only way they know to talk about scale, which is lots of different ways, but none of them having to do with physical scaling laws. So it really hit me last week that this was such a key level of understanding that if I have to hear one more person saying we just need to scale up this, if we could scale up graphene, we'd solve all kinds of problems in architecture. Sort of not really, realizing that there's a huge difference in the way that we see the world, in the way that we talk about the world. Misgovernance, this is a real problem on this. This is some years ago, not too many years ago, I did a session at one of the Conference of Parties meetings about building energy use, and what was sort of bizarre about this thing is they had 200 side sessions, of which only 3 dealt with buildings. Even insofar as pretty much every policymaker up there was showing a slide like this about how important buildings were to energy. And of course, one of the questions I got while I was there was, why would an architect, be here at this meeting, this meeting critical to the world future on climate, but yet they would show this type of slide about buildings. And this belief exists, and we see it in almost everything that comes out on a policy document. And one of the things I noticed as I was sort of reading through policy documents is I saw a phrase basically like this: energy consumption in both new and existing buildings could be cut by an estimated 30 to 50% through readily available technologies, design, equipment, systems, alternate generation solutions. And sort of like you can begin to see, I looked at that and I said, I don't understand where that came from because I don't know what those technologies are. But if you go to like the McKinsey charts and you go to many things like that, they know what they are. It's insulation, it's lighting, it's air conditioning, it's water heating, and of course standby losses. So pretty much buildings should save the world, and it's a win-win. It's low-hanging fruit, it's a win-win, you get savings from that. And again, I think I don't know how they're doing their calculations on this. And so I started reading these different documents, and I've read them in different countries, I've read them for different institutions, and they all had that quote. It might have been slightly modified, but they all talked about 30 to 50% savings could be gotten by using readily available technologies. So if you do a paper trail of this, and you do a paper trail of that particular statement, and you kept going back and you kept going back and you kept going back, it went back to a 1992 study of 11 buildings in a Southern California development where they were looking at very particular technologies at a very particular time on this. And every time it was cited, something would be dropped off of it, a little bit of it. Nothing was disingenuous. It was just like, well, it wasn't houses the next time, and it wasn't, 11, and it wasn't in Southern California, and, it wasn't built at a particular time, and it just became fact. But the problem with this fact is that it is driving policy worldwide. It's driving sort of where incentives are, it's driving policy. It's also part of the thing that when you talk about trying to get research funding in architecture, it's like, hey, you guys don't need research. You just need to do your job. And actually, I had this conversation with John Holden before he became Obama's energy czar that he had a position for a while. And he was explaining why things were so complex in his area. And then he turned to me, he says, you have it easy. All you have to do is insulate a building, and you could fix so much of the world's problems. But that's the sort of thing that's been carried through and that we deal with. This, I think, is a sort of a real key to it. This is the Department of Energy's proposal for replacing LEED. It's their Builder's Challenge. And when I was going through how they did their calculations, I was really taken by the calculations on cooling. Because if you followed their calculations, first of all, the bizarre part of this, as most people who work on buildings know, is a building cannot be considered energy efficient or LEED certified unless it has a dilution-based mechanical cooling system. So if you do natural ventilation or you don't use cooling, you don't qualify for being, energy efficient. So first of all, you have to have a system like that. But when you worked through their particular calculations on it, you would have put in a system that was about 50% larger because they want it designed in a home to laboratory standards. They chose, very particular sort of like factors of safety. They chose a very particular type of climate model, all of that. And I finally called them. I said, where did this come from? And I should have been able to read it in here. And so this is also where many of our things come from, that we really don't have anybody out there sort of checking. And again, nothing's disingenuous. It's just sort of a nature of, the fact that so much of what we do is so very diffuse, so spread out among so many different types of people, that there's not the kind of governance there's not really a defined discipline if you're working in between disciplines, so it doesn't have the kind of governance that you might find in more defined disciplines. So when I call these disciplinary translations, I'm not talking about these as good examples, because I think that they're indicative of much of the same kind of incidental nature of the others, and I don't want to talk about the others as being bad examples. They're simply the way things are, and we have to understand that that's part of the problem space that we deal with, so all of them actually contribute to understanding the problem space. But this is just a couple of projects, one that in particular that I've been involved in, one that is somebody we hired at Yale because of his involvement in a project, but just sort of different ways of thinking about coming across disciplines. This first one is this project I did with electrical engineering at Yale. And like everybody's seen these dashboards to death, about how energy is used in a building. And this was with Andreas Savidis, who was thinking that he could really break down and analyze circuits, not just a lighting circuit, entire circuit, not just sort of like the fans and pumps and so on, but actually take particularly the plug loads and pull those apart, break them down in a very fine-grained look at what was going on. And, we ended up outfitting a building. Rosencrantz was the building we outfitted, and started comparing the information that he was pulling off by looking at the building management system. And if you haven't seen a data dump from a building management system, it's pretty astonishing when you start to see all the different points that are being monitored, all the different points that are being alarmed. It's such that even a very well-educated facilities engineer has a hard time sorting through this, and we're in a day and age where facilities, managers and engineers are the first things to go at institutions. So you have these reams and reams of data points being dumped. We have something like this. You don't have anything in between that. And so I realized, we were having a number of conversations, and one of the things he wanted to do was that he wanted to break this down, but just the electrical part of it, down to the point that he could sort of even take a house and sort of connect dynamically to the grid and know when and how on a real-time basis to shed loads. And the only way you could know how to shed loads is if you actually sort of were able to break down the micro-scale use of it. Except that the majority of it was probably sort of the standard use, but actually began to sort of really look at what was happening on the micro scale of it. And so when he first approached me on this, and I said, well, just because this involves buildings doesn't mean that I'm interested, because I don't do anything in electrical engineering. But the more he talked about it, the more I realized that this was sort of like a kind of an incredible moment for us. And what it is, if you sort of look at how the two teams set up, so based under utility market dynamics, this was his interest over here. But I realized that every bit of information he gathered, plus the sort of his algorithms that he was developing in order to break down circuits, would help us develop a new building metric. Because right now our building metric is about as clumsy as they come. Energy per square foot, which is a bizarre way of thinking about buildings because it privileges the large building. The bigger you make the building, the more you're spreading out, occupant loads and personal loads so they look better. The way you can make a building look as energy efficient as possible is slap an atrium in it. Anything that gets rid of people really makes the building look energy efficient. So, and it's clumsy because everything gets cobbled together into this energy per square foot. So, I started taking the data, and the idea of the data was to really rethink the metrics. And of course, by rethinking the metrics, the things it could spill into. And so this is just sort of like that first sweep of the metrics as a 4-part metric for a building, looking at things that are per capita, that shouldn't be thought of as about per building, but per capita, things that are really about the individual pieces of equipment or the individual technological systems, things that are about the way we design a building, which is the interior conditions, lighting design, interior climate design, and then the last thing that's in there is the envelope. And it turns out when you start looking at information, particularly for not a house, but you start looking now at, this was a medium-sized institutional building, the envelope is one of the most insignificant parts of it, and yet the envelope is the thing that we really focus on. So this was something that, neither of us really cared what the other were doing. I sat on all of his postdoc and student reviews, and I basically had to paste my eyes open because I really didn't quite understand what they were talking about. They really didn't care about buildings. But there was something about that relationship that allowed him to form his own company and allowed me to sort of begin to propose nationally and internationally how we might need to rethink the way we look at buildings. So it's one of those types of relationships that they describe more as multidisciplinary. We're kind of working in parallel. We're piggybacking off of each other, and we're sharing work with each other. I got a huge amount out of this one. But again, if he had not come and bugged me in my office trying to get me, he needed another discipline to sign off to get this grant. And if he had not bothered me, I never would have known. I always knew that I didn't like that metric. I just never knew how to go after it before we sat down. And this is sort of one that I also find sort of an indication of a strange opportunity that we've missed. As you think about lighting design and you think about sort of the advancements in lamps and particularly toward LEDs, how strange that we would take something like an LED and think it should be used as a replacement for fluorescent lighting, used in the same way as fluorescent lighting. Now you're dealing with something that wants to operate a DC current. It has sort of incredible angle control. There's so many things that you can do with LEDs that you cannot do with conventional fluorescents. And yet, just like with the Department of Energy, micro pumps had to be just like an HVAC system, we expect any new lighting technology to be just like whatever archaic technology we have. And you compare with probably the next most archaic technologies, which would be anything for the automobile, they at least get how you should use lighting on here, but you actually use it to see, not to sort of fill up huge volumes of spaces, but actually to see. So this relates to the project that started at Harvard, and then we scarfed this guy up and brought him to Yale a year and a half ago. People probably are familiar with this really fascinating project that took place at the Fog at Harvard. These Rothko murals that had been misstored, badly faded. And so the discussion is that if we restore them, we lose the integrity of the stroke. We don't restore them, we don't know what they really, we can't recover what they look like. And so Jens Stinger realized that what he could do is actually, with a very well-designed projection, create the mural again on the mural with light. So you can see here, part of the programming for it. So an hour a day, they actually turn it off so you can see the actual condition of it. But as far as the eye is concerned, that's the mural. It's the light coming off, it's the light hitting your eye, that's the mural. So we hired him. We brought him to this Institute for the Preservation of Cultural Heritage. This is a place that I mentioned before that had the reversed skylights. And he wanted to take it in almost the opposite direction, which is really interesting, is that rather than sort of thinking about how he could recreate the image that we saw, he wanted to sort of come back and redesign the lighting fixture itself so that the curators, the people doing preservation, had not only incredible color and contrast control of every artifact that they were looking at, but that, if you know much about dealing with certain types of artifacts, they're extremely sensitive to not just the wavelength of light, but to the amount, the sort of like the hours of exposure and sort of the power of that light. And so he looked at the film industry, because we may not be doing anything with LEDs and digital lighting, but the digital cinematography is. They're doing incredible work with sort of looking at ways to digitally light film. So he went into there, and they ended up working with Philips in order to sort of develop this particular light fixture that was ideal for conservators. And here's the amazing thing about it. It's half of the energy of a conventional lighting fixture, except it has pure, perfect color rendering, perfect contrast control on that. And as a matter of fact, he used that light to restore this particular Velasquez. If you follow art, this was found folded up in a basement on campus. And he was sort of led the restoration of it by having that kind of sort of like, backward working of light. So he sort of flipped around in many different ways to gather things. I would not have known of it had I not been on the board of this particular institute and happened to be over there that day when he was in that day and wanted to chat about that. But the implications of something like that for rethinking lighting and architecture, astonishing. So purely accidental to find out about it, purely fascinating from his standpoint that he began sort of mining different ideas out there. And these last two are just little fun things. Trying to get students away from thinking that everything belongs to the artifact. This was my second generation of the smart materials class where we dealt with light. I had one student who built a series of headpieces that the students wore around, trying to sort of understand how light intensity, light distribution density, contrast sort of like was what determined where a surface was. Where the surface was doesn't determine where it is. It's actually how the contrast sets up in light. So you'd put on a headpiece like this, and this area here, you swore it was 50 feet away. And so it was just sort of fascinating to do that. It was a great demonstration to get them away from thinking that everything is about the surface has to be right there. It's actually about the phenomenon and how the eyes worked on this. And this last one is going to look like it's so unsmart you can't imagine, but I think it's smart because it's so dumb. This is a project when I taught in Germany a couple of years ago, and I taught a studio on basically dealing with phenomenological installations. Corrected on this because I was told that I was supposed to teach a studio on either masonry, wood, or concrete building, not on light and installations. So I had an interesting group of students who decided to take the studio. This is still my favorite project from that studio. So it's a student who worked with paint, highly reflective paint and a projector in order to create a window. A seeming virtual window in this very dark, what is a normally very dark underpass on campus, on the campus of the Technical University in Munich on there. And he did a series of these installations on campus. Again, if you don't have light on the particular paint, you don't read it as being anything other than what's there. It's not white paint, it's just the way that it reflects and the directionality of the way that it reflects. But an idea of making smart the phenomena and letting the artifacts, letting the building be dumb. To me, that makes a really smart building when you think about what it does as opposed to sort of just what it is. So on that note, and I don't know if you have time for questions or we should take time for questions.
That was a great talk. I have a question about fragility. I mean, most of the time when someone designed a building, they have something in mind, and 5 years down the road, everything is out the window, everything changes. For example, I worked in an atrium. Initially it was an atrium, but they ran out of space, so they put us in the atrium, and they had this glass on top, because it was supposed to be an atrium, but when it snowed, it was getting extremely cold up there, and you had this circulation. Can you comment on how you can put in that kind of stuff into the design so that you don't end up designing something that can only work under one unique situation? And
I probably can't do that, not because it's not actually a very important question, but it is sort of one of these fundamental questions that has been at the heart of a lot of both education and writing about architecture for years, is sort of this role of adaptability and this role of flexibility, this role of thinking for the future on this, that even some of the people who have been sort of the most future-minded have cemented into place some of the most sort of unforgiving elements in buildings that are very difficult to deal with. I suppose I'm going to cop out on this by saying that I want the building to get dumber. The dumber the building gets, and the more that you use, whether it's phenomena or sort of very discrete technologies to do your functionality, then the more opportunity you have to be flexible. I say that's a cop-out because we're kind of not really there yet, so it's easy for me to talk about it rhetorically and not actually show an example of what that might be like. But I do think that this is something I've spent a great deal of time talking about was I don't necessarily want to see a smart wall. I don't want to see a smart this. I want to see a dumb, simple stuff, and then find ways to sort of like deal very discreetly with certain types of interventions so they become nimble, they become transient, they become light. Whether that really solves the flexibility problem, I don't really know. But I do think it's a way to make buildings sort of less energy intensive because you're no longer sort of like dealing with the entire building being conditioned. You're actually sort of dealing discreetly with where you need things to be done. So that's the best I can do with that. But it is a very fundamental question that many, many people have wrestled with.
Over 20 years ago, Stuart Brand indicted the entire architectural profession for notoriously designing things which didn't work and never revisiting the premises to learn from their mistakes and thus repeating them over and over again. And coupled with the fact that architecture tends to be quite faddish, certain things are in for a decade or so and then less so, is it your perception that the field has gotten any better at not doing this?
Wow, I have to speak for the entire profession. It's a little scary on that one. You know, I mean, I think something to keep in mind, a couple of things to keep in mind. One is that buildings, you know, generally last 50 years or more. So you don't really have, you know, that kind of turnover as things shift. Another is that, and I think you might know figures in Europe better than I do, but in the US, I think the number is 9% of buildings are done by architects. The vast majority of our building stock is fairly sort of like, you know, quotidian stuff that's just constructed, but not actually architecture. Granted, the stuff you have coming on campus is done by architects as what we have, and I can sort of go on both ways on the stuff that we're getting built at Yale as well. One of them by my boss, and then, you know, others sort of like great buildings of that. So I think that's more something that I don't know that I can speculate on all the reasons for that. You know, I will say that perhaps a little bit of defense of the profession that, and I think it's probably also an indictment of me tonight, it's really easy to sort of see where we went wrong. It's really much more difficult to see what's, you know, what are the persistent elements that we have to be thinking about, all the things that are underneath this, all the social things that you're thinking about, all the political things, all the economic things, all the cultural things that have to go into the way that one thinks about a building, including, you know, its cost, its safety, and so on. So the pragmatics as well as many other types of agendas. So I think that I can't give you an answer for that would be satisfactory. But I do believe that much of what's happening in architectural education today is a sort of return to the thing, the return to how we make things, the return to materials, and the return to systems. I mean, you have it here at Princeton with the people that you've hired in architecture, you know, bringing a type of rigor to certainly the technological aspects of it. I think that's happening in the field, and I do think we sort of swung the pendulum one way for a while when we really had an important political agenda to deal with, you know, for you know from the 60s on. So I don't think I can give you a full resolution of that other than I'm hopeful, hopeful for the future. So.
How could you promote the idea of dumbing down buildings, making them less smart, so that in order to make adjustments...
Make them smarter.
Yeah.
In order to dumb down the armature of the building, yeah. To make sort of like the discrete elements smarter. How can I promote that?
Yeah, how would you promote it? I mean, you know, everything nowadays is smart technology and so forth.
Well, that's what I'm hoping I'm going to deal with in this damn class this fall, is sort of like really put that question out there. I have lectured a lot, you know, in different parts of the world on this, and I think everybody enjoys the lecture and then goes back and works on a smart wall type of thing. So I think this is part of my question today, is what is that gap where I think people like the argument, I think they like the discussion, but where are we not filling in the gap to actually allow this to exist in that same realm? So that's my question for you guys.
Well, how about appealing to the cost aspect, you know, to homeowners, houses? I mean, so many houses nowadays have extra rooms, okay? Or maybe there may be sometimes during the day when rooms are used and other times during the day when they're not used. How about appealing to the cost-saving aspect to homeowners, you know, so that they would put on their thinking caps and realize that there are much more efficient ways to operate the electricity and you know, the air conditioning and heating in their house?
Well, I think one of the ways that I try to get students to think about this is that, and this is something I've always done in my smart materials class, is that after they've sort of, you know, developed the coolest thing ever, then they have to go back and imagine it in a developing country made with conventional materials. That if they can, instead of thinking about it as about being this project, this building, but instead sort of like larger and broader implications, that, you know, whatever we're doing now, even, you know, our tiny little movements that we're making towards saving energy now are sort of going to be completely eclipsed by what's happening in the developing world. And we need to not be thinking about ourselves, but also thinking about how we can contribute to that. So that's the way that I would go after that, is actually having them think bigger than themselves rather than, you know, about their own homes.
I didn't quite get your discussion on the concept of a building envelope being the inside of a building being thermodynamically isolated from the outdoors, and that it's sort of the wrong way of thinking. Are you arguing that the thermodynamics should take advantage of what nature has to offer? There should be some interaction between the indoors and the outdoors, as opposed to let's isolate this conditioned space and operate from there?
Yeah, I think it's going to go on an entire range, you know, anywhere from something like that, which I think is a first level of mediation, all the way to understanding that these systems exist for one reason and one reason only, which is the human body. And yet, you know, we pretty much light anywhere that the eye can't see, you know, about as inefficiently as you can. But if you can think about LEDs and the opportunity to actually sort of direct light only where it needs to be directed. So what I'm thinking about is sort of that I don't want to light the building and I don't want to heat and cool the building. I want to think about the body's interactions with its local environment, so contingent interactions with its local environment. So, you know, light in the direction I need to see, thermal exchange with my skin, as opposed to blanking myself in this sort of, you know, huge volume of air, that the body really, it's about an inefficient way of dealing with the body, both lighting and heating and cooling. You could not pick more inefficient ways of dealing with the body's energy exchanges. So it's really about saying it's not about the building, it's about the building being an armature for how the, you know, the systems that can interact with the body.
Thank you. Sorry. You made a brief reference to political agendas coming out of the 60s. Could you elaborate briefly?
Well, I think, you know, I'm a, you know, more of a technology hound and then a political scientist, but architecture was very much affected by, you know, what happened in 1968. Matter of fact, we even think about our theory as pre-68 and after 68. You know, you think about, you know, the sit-ins at Columbia, but you think about what happened in France and all of that. And there was a very different sort of sense of political agency that architecture took on for itself after that time period. You know, also in trying to understand what it was as a theory base. You know, and where does that theory come from? Well, you know, we don't have an inherently own autonomous theory base. So the theory was coming from a variety of different areas that were being put. Yeah, well, that was certainly, you know, one area. You know, looking to literary criticism, there's a whole variety of things where architecture was trying to find a deeper discourse for itself. So we marked that in 1968. But that's not my area of expertise. I teach all the courses nobody wants to take in technology, so not the theory courses or the history courses. Somebody has to do it, yes. That's where the big bucks are, right? Yeah. Probably every student in here in architecture could answer that one a little better than I could.
Yeah, especially in the urban area where maybe the price of the land is very expensive, and maybe the need for building a small houses for even poor people in the developing countries, and with the smart technology like Internet of Things, do you see more and more like utilization of the movement within the house or within the building to optimize, say, the electrical use and so on, like the motion type, the movement of the room, on the rearrangement of the continuous rearrangement or dynamic of the space arrangement, for example?
So are you talking about, I mean, when you say dynamic, are you actually talking about
for example,
things
maybe the
moving,
roof trying to optimize with the sun incoming light, and maybe the space movement so that maybe larger space available for small houses, for example? Do you see that kind of movement with the Internet of Things?
I don't know that I see that as a movement, but I also see that as actually a very interesting way of thinking about contingent environments. You know, this sort of idea that I don't sort of like belong to this sort of physical structure of this room. I belong to this moment in space, and that moment in space is contingent upon a series of different events that are happening. They might be thermal events, they might be sun, they might be, communal events. That could be many things, but I don't know that the walls have to move or the furniture has to move, but if we can begin to sort of even use that as an idea, I think it goes back to this idea of the building as a simple, dumb armature, and that allows all this kind of sort of movement and flexibility within it. So while I don't necessarily see that coming, I think it's one of the things that helps us reimagine how we might be occupying spaces.
When you say dumbing down the kind of fabric of the building, does that mean to you not having it consider sustainability at all, so that sustainability comes purely from technology, or is there still a place for the fabric of the building to have a kind of passive, more vernacular contribution to that?
I think it's actually both of those. I think it's from the standpoint that, I mean, I'm first very interested in decoupling energy environments from the structure of the building. So decoupling thermal environment, from the envelope, decoupling light, from the ceiling. And that's part of the dumbing down, is sort of allowing that to be a simpler armature. So it ends up, my hope on one side of it is that the embodied energy goes way down. When you're no longer sort of dealing with super insulating things, when you're no longer dealing with a lot of these types of systems, the embodied energy should go way down. And then if things can become more discrete, then they will, de facto use much less energy. So it ends up being an indirect way. So the question that I think you have in there is that, does it demand very advanced technologies to do the discretion? And I think that's a really important question. Certainly when I started my original research, I really was planning on using micro machines, and then it shifted to where I was using the little, Peltier devices like this. And then the last set of things that I did, I actually just used halogen lamps as a way of sort of shifting the characteristic length. And it's actually not so bad. It ended up going into tuberculosis work. So that was a way of getting, the advanced technology gave me the idea, but in the same way that I asked students to rebuild things with conventional things, I think that then you go back and you start to deal with the things and the tools and what's at hand. So it shouldn't demand the advanced technology. The advanced technology should facilitate thinking in a broader way. But my hope is that actually we would, I love my high-tech stuff. There's no question about it. But my desire is that actually would sort of like background, that we start thinking about the instrumental behavior as opposed to the tech itself.
So I guess, as usual, as the host, I get to have the privilege of asking the last question.
I think that you have the privilege of taking me out for a drink. I think
Yes,
that's what's
that
supposed to
too.
happen. Yeah.
Yes. So there is, I believe, food outside.
Okay.
So the last very simple question would be if you could give the engineers and architects, us sort of having to play both sides of the field, any advice for the discourse that should exist between the two. I mean, what is your most, we had an interesting start to the day talking about how in engineering school lecture series, we get a very nice programmed out day meeting with people. Some of you got to meet with Michelle today. But in architecture schools, you just get plopped down and maybe you run into somebody in the school, right? So I think that's, maybe you can...
It's a lot less time consuming, that's for sure.
Yeah. So maybe just sort of the peek into the other world, what would be your peek that you would give the audience?
I don't know that I can actually sort of give a reasonable peek, but one of the things I enjoyed about this debate last week, other than when Joanna was there, was when there was a material scientist who was listening to architects sort of talk and said, "Does rigor exist in your profession?" And this wasn't sort of an indictment of what we did. It was actually sort of like laying something out like, well, how do you identify rigor? And I have to admit, we had an incredible discussion for the rest of the two-day symposium, going back and forth on what rigor actually meant in the material, in the construction world. I think those are interesting questions. So, we can all be critical about how architecture is built. We can all be critical about certain advancements in other areas. But I'm really interested that in questions like that what it was not meant to be critical. It was actually a question of curiosity on that. That's what I would encourage. I don't think that didn't answer anything, but hey, I haven't had my drink yet, so that's what.
We can all talk about rigor
Yeah.
outside, so let's
All right.
thank Michelle again.